Thank you all. So as I said, we're from Intlvac. We're a thin film coating equipment manufacturer and coating provider in North America. We have offices in Canada and in the US. Our core fields are metal coatings, fiber metallization, indium solder bumps. This is the reason why we're here today. We also do ion beam etching for delivering, ion figuring, optical coatings, both for infrared and visible materials, well, applications. And then we have diamond-like carbons also for the IR and some topological coatings. So indium bond, we had for flip chip bonding, we had a great introduction from Travis at FinTech before. It was quite a journey for us. So it's a journey that started about 10 years ago, where we started by having indium bonds that look like this, and they're not; those ones are not great. In between, we've learned quite a bit, and I want to share with you guys what we've learned throughout the journey. And you would say, well, indium bump, how can it be difficult to evaporate indium? I mean, it melts at 150 degrees. What can go wrong? Well, hopefully we'll show you a little bit what we've learned. In the road, we got a patent, but we keep going, and we're still improving the technology, and we intend to continue going forward. So just on the key points that we'll talk about. So the first thing we focused on was optimizing hole closure to try and get bump as vertical as possible. And then two things that we had to suppress, which is dendritic growth and then prevention of splits. And then I will talk about the stability, reliability of the systems, and then some more about the indium bumps we produce. So why do I talk about hole closure? So here on the left, you see a typical indium bump. So you have a wafer, you have your photoresist, you deposit indium. So indium will come on top of the photoresist, and then eventually what you would want is your indium bump. The indium on the top, you will remove it during liftoff. Ideally, you would want your indium flux to be coming perpendicular to your substrate. But in the reality, you will have some part of your flux coming in this yellow arrow. And the problem with this is it will come on your sidewalls, and your sidewall will grow inward, and your hole closes, and so your bump moves and gets smaller at the top. So one way to prevent this is to really try to avoid any off-axis flux. And the way we went against it is to increase the throw distance between your evaporation source and your substrate. And you can see, so the further away your substrate is, the more the flux comes at a perpendicular angle to it. And so we ended up with a throw distance of more than 1 meter. How does it look like for systems? It gives you a system that is a very tall chamber, as we see here, where you go from the back at the back of the system to load substrate on here on the load lock. And here's the 200 millimeter substrate. And then with this throw distance, we have another advantage. That is that we have inherent uniformity. So here we show on the 200 millimeter substrate, we have a plus minus 5% without having to move the substrate at all. So nothing moves during the deposition, which has multiple advantages system-wise. But it's not sufficient just to have good directionality and uniformity. I was talking about the other problems that you have. So dendritic growth is a big one, is a big classical one. So if we look at this is a SEM image of a patterned wafer with indium, and you can see it has cauliflower-like structure, and more than the cauliflower structure, you can see all those dendrites. That this is an extreme case where it even bridges all the way across. So this is something that you want to avoid. To understanding what's going on when this happens. So if I go back to a schematics where here we have our photoresist in red, or indium growing at the bottom on an imaginary substrate here, and then growing at the top, what we understand is that indium really wants to make crystals. And if it starts forming a crystal at the edge of your bump, and that crystal happens to not be perpendicular and it's sideways, as it grows, it will just grow and grow more and more and shadow the holes, and it will get a lot of the flux coming into. And then you